Howdy everybody, it's Michelle here, and we are going to run through a hand computation of an independent and a dependent t-test. We're going to be using this pretend data set here, where there are two groups, group 1, or GP for short, and group 2. And group 1 has 5 observations, group 2 also has 5 observations. The first thing that we're going to need to do for the independent t-test is we're going to have to compute the means and the variances of these two samples of data here. So I'll start from scratch, just in case. It's been a really long time. And we'll begin with the means. And to emphasize, we're going to start with the independent t-test. So that's what we're preparing to do now. So for group 1, mean 1 is simply equal to the sum of all the observations divided by the number of them. Here, that's 9 divided by 5, which is 1.8. So the mean of group 1 is 1.8. So group 2's mean is 3.2. So because the standard deviation is a very helpful descriptive statistic that explains to us how data is spread out, we're actually going to compute the standard deviation, even though with t-tests you could compute the variance and use that. The variance is just the square of the standard deviation. And as a note, we're going to use S for standard deviation. That means that we'll be able to use S squared for variance, either of which, as I mentioned before, can be used in a t-test. So for the first standard deviation, I'm going to compute it at a fairly normal speed. So if you need a refresher, I invite you to follow along, maybe work a bit ahead. So for standard deviation 1, the way that looks like with all the notation is it's the sum from observation 1 to 5 of the individual observation, which we call x sub I, minus the mean of group 1, and we square those. So sum of squares on the top, and everything there is divided by not n, but n minus 1. So in this case, n is 5, so we'll be dividing by 4. And the mean is, of course, 1.8. So more specifically, we're going to be looking at gigantic square root sign. And we're going to add 1 minus the mean, 1.8, square that, then add that to the next observation 2 minus the mean, 1.8, square that, and do the same for the remaining 3 data points. We have 1 minus 1.8 again, and since I'm running out of room, I'll just kind of stick this all on 2 lines. I think you know exactly what I mean though. 3 minus 1.8 squared, and another 2 minus 1.8 squared. Perfect, and that whole thing, as we discussed, is divided by 4. So, because I'm a fan of showing my work, I'm going to start another line here, and I'm just going to show you my computations of these squares before we sum them. So I get 0.64 for the first one, plus 0.04 for the second one, plus 0.64, plus 1.44 for the big one, and then once again 0.04, and I'm going to divide all that by 4. Can you guys see that? Okay, good. And that's our square root. So continuing from the last line, when we sum all that stuff up in the numerator, we get 2.8, and we're dividing by 4, and that gives us the square root of 0.7. And when you take the square root and you round to 3 decimal places, you get 0.837. I just wanted to bring your attention to the fact that sometimes when you square root numbers, they don't get smaller, they get a bit bigger. This actually happens with decimal type numbers like 0.7, 0.3, those types of numbers that are pretty close to 0. When you square root them, they actually get a bit bigger. So don't worry if that happens, it means you're doing it right. I want to make a note too that we shall agree to keep 3 decimal places while we're working, and that means that we'll avoid too much rounding error that could come into play when trying to compare our results with those in SPSS, because in SPSS, when they do the computations, the computer stores many decimal places at a time. So I think 3 is a reasonable amount. So we want to add that there for group 1's standard deviation S, and I'm going to do S2 as well. It's just going to be a speeded up. So feel free to make sure that you are 100% on board with that computation, and then we will continue. Alrighty, welcome back to normal speed. So as you can see here, when we computed the standard deviation for group 2, we got the same exact number as we did for group 1, and so we'll add that to our summary statistics. And so that does not need to happen. That happened because I did that on purpose, so just to make a quick note. The idea is, of course, the standard deviations need not be equal, and very often they're not going to be. Okie doke, we're ready to start our t-test computation. For the independent t-test, that formula looks like the difference in means on the top. I'll just write in the order x1 minus x2 bar, and we're going to divide that by the square root of the variance over the size for group 1, and add that to the variance over the size of group 2. And before we continue, one main goal for us is to understand conceptually what the t-test is doing. So what the t-test is doing is it's looking at the difference in means. And as you can see by the summary table, that difference is, well, it's like 1.8 minus 3.2, or 3.2 minus 1.8 if we had said x2 bar minus x1 bar. And that is, oh man, math on the spot, and I can't handle it. Okay, wait. So if it was 212, 1.4, I think it's 1.4. I'm scared. So the idea is they differ between each other by 1.4. And is 1.4 an actual significant difference? Well, it depends also on how the data is spread out. So what this does on the bottom, this whole thing, including the root sign, this is computing the standard error. Okay, the standard error, one way of looking at it is it's an estimate of how close the difference that we found in our two samples is to the true difference in means at the population level. That's just one of many ways to describe a standard error. The standard error is kind of a tricky sort of concept, and so we'll just have to keep practicing describing what it is and looking at it in various ways in class and otherwise until it makes some more sense. So now that we have this formula and we somewhat understand the components, we're just going to sub in the values. So t is equal to mean 1 minus mean 2, and then we're going to divide by the variances, and it's like, I'm gonna do it like this. Okay, meh. So divided by the square root of, so for the variances, we have to take the standard deviations that we computed and square them, dividing by the number of observations in each group. So the problem is that we could have just kept our variances and not taken the square root. So I think it was 0.7 that would have been the variance for group 1 and likewise group 2. And so we're kind of undoing what we did before. We're doing it the long way, but as I mentioned before, I think the standard deviation is an important measurement that we should kind of keep in our minds when we're looking at descriptive statistics. It doesn't hurt to get a little bit of extra practice with subbing things into formulas or computing square roots. So that's kind of our justification for that. Okay, so simplifying a bit from the last line, we have t equals negative 1.4, and that's divided by the square root of 0.140 plus 0.140. Okay, cool. And simplify further. Negative 1.4 over the square root of 0.28, and that's equal to negative 1.4 divided by 0.529, and to 3 decimal places, that is 2.647. So that's our t-value. Now we like to compute the dependent t-test with the same data that we're using, just under the interpretation that the data are paired. The first thing we might want to do is take a look at the formula for t-test for paired data. So what that looks like is a little different. Instead of x1 minus x2, the two means, we have this big D bar. So this is a different kind of mean. And then we're dividing that by the square root of, it's a variance, but it has to do with this quantity. And we divide by n, where n is the number of pairs of observations. So just like last time, we want to understand conceptually what the numerator and the denominator of this test are about. So this here, before we said that it's the difference of the two means. This time, when the data are paired, it's a different quantity. What this is it's actually the mean of all the different scores that you can make with our data. If you don't know what that is, that's great, because we're about to compute them and then it will make sense. And then this here, just like before, is the standard error, or SE as we like to denote it. And again, what this quantity is doing is it's assessing how close this mean of all the different scores is that we were obtaining from our samples is to the population mean of the different scores. It's kind of a way to see how close our sample is to estimating the population, in a sense. So the first thing we're going to do is we're going to compute what this mean is. And in order to do that, we're going to compute the different scores, and that will illuminate a bit about the nature of paired data. So a very important part of the conceptual difference between an independent and a dependent t-test is how that difference in means, or the mean difference, is computed. The idea here is that before, with the independent t-test, we're looking at group 1 and group 2 as completely independent samples, which means that 5 participants were randomly assigned to group 1 and another different 5 were assigned to group 2, and they give us these observations. In this case, now that we're assuming that the data are paired for a dependent t-test, what's important aren't the scores themselves. It's important what changed between them. So, for example, we have participant 1 represented by this row, and their score, say before, was 1, and then after treatment was 2. And so what's important is that they went up from 1 to 2, not that originally they started at 1. Same with this person. This person gave us 2 measurements, before and after. But what's important isn't the fact that they had a 3, which happens to be the highest point in this data set. What's important is that they didn't change after treatment. Their score remained the same. So D represents a different score for each of the rows, that is, for each of the participants. So computing that, so one thing you might have noticed is 1.4 is the same as subtracting mean 2 from mean 1, or it's the same number that you get when you go mean 1 minus mean 2, as we did with the independent t-test. Why is this? So the reason why in some cases you end up getting the same thing with the different scores is because we have the same number of data points or observations in both groups. So what's really different when the groups have the same amount of observations is what's happening in the denominator. Next, we're going to find the standard deviation of those different scores. I'm going to set it up for you. So we'll have SD is equal to So as you can see, this standard deviation looks a little different from the standard deviations of the groups when they're viewed as independent. So now that we have our D bar, which is 1.4, and we have our standard deviation of the different scores, which is 0.89, we can put that all into our dependent t-test. All right, so write the formula down again because we're now ready to work with it. So T is equal to mean of the different scores divided by this standard error here, made of the different scores variance and the number of participants providing observations. And when we sub in our numbers, we get 1.4, and that is divided by the square root of 0.89 squared divided by 5. Continuing to do maths, we have 1.4 divided by the square root of 0.178. Remember, we're just going to carry 3 decimal places through. If you want to carry more, feel free. They get heavy, so just carrying 3 is fine for me. And that is equal to 1.4 divided by 0.422. And so, in conclusion, the dependent t statistic is 3.318, rounded to 3 decimal places. Okay, we're ready to wrap up and gain some more conceptual understanding into the differences between these two t-tests. So when we did our computations all by hand, we found that the independent t statistic for group 1 and group 2 was 1.4 divided by 0.529, and that was about 2.65. However, when we viewed the data as paired, we computed our different scores and then our dependent t-test, we found that that was equal to 1.4 over 0.422, which was about 3.32. So the dependent t-test then is quite a bit more large or higher than the independent t-test. And so just looking at the same data but in 2 different ways gives us some insight into the fact that when you focus not on the individual scores in either group but on the change between them, you end up eliminating some of the error that can come out of people being different people, because the same person is providing your before and your after observation. So one last thing to keep in mind here are the degrees of freedom associated with these two tests. For an independent t-test, the degrees of freedom are equal to n1 plus n2 minus 2. So in this case, 5 plus 5 minus 2 gives us 8. However, for the dependent t-test, there are only 5 participants. So the degrees of freedom associated with that end up being n minus 1. And that's just equal to 4. Sometimes you might see that because the number of participants in this case ends up being the number of data points, because 5 data points ended up making this mean, you might end up seeing big N minus 1 being used. So this is saying the whole number of observations is being used because the whole number of observations is actually those 5 difference scores that made up D bar. So just to clarify, n minus 1 is correct whether you're using a little n or a big N here. That is not the case here, because the big N for this is 10. And here again, it's 5 minus 1.